Late September 1944, Kummersdorf Proving Ground, Brandenburg, Germany. The American flamethrower sat on the testing bench like an accusation, its twin fuel tanks still bearing scorch marks from whatever Pacific Island hell it had been captured on. Engineers from the Wehrmacht's Chemical Warfare Service gathered around this prize, notebooks already in hand, trying to mask their unease with professional detachment. This single M2 flamethrower, captured intact during the final Allied push through France, would trigger a crisis of understanding among German weapons specialists that cut deeper than any tactical defeat. The mathematics of incendiary warfare were about to be rewritten, not through superior engineering or theoretical advancement, but through something the Germans had never fully grasped: that American industrial philosophy valued brutal effectiveness over technical elegance, and that sometimes the most terrifying weapon wasn't the most sophisticated, but the one that simply worked when you needed it to kill. The weapon bore no markings beyond its serial number, stamped into the pressure tank. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. M2O-2, manufactured by E.C. Brown of Rochester, New York. Built by civilian contractors using automotive manufacturing techniques and belonging to the 4th Marine Division, this flamethrower had traveled from an American factory to a Pacific battlefield to a German testing facility, each kilometer of that journey representing a gulf in military-industrial thinking that German engineers were only beginning to comprehend. Oberingenieur Klaus Richter lifted the weapon's gun assembly, feeling the weight distribution, examining the simple pipe construction and the two-trigger system. For 20 years, German flamethrower development had pursued technical refinement, hydrogen ignition systems, precisely calibrated fuel mixtures, sophisticated pressure regulators. This American device looked like something assembled in a factory that made farm equipment, heavy, utilitarian, unsophisticated. Yet, intelligence reports from both fronts spoke of its devastating effectiveness and its unnerving reliability. The M2 weighed 68 pounds when fully loaded, heavier than Germany's current Flammenwerfer 41 by nearly 30 pounds. German doctrine emphasized mobility and tactical flexibility, keeping weights down, training elite assault pioneers to handle delicate equipment with precision. The Americans, it seemed, had simply accepted that their Marines would carry more weight if it meant the weapon would function under any conditions that combat could impose. At Kummersdorf, located 25 kilometers south of Berlin, German weapons testing had reached a peculiar stage by autumn of 1944. The facility had tested captured Allied equipment throughout the war, analyzing everything from Soviet 34 tanks to British Churchill infantry tanks, documenting strengths and weaknesses in exhaustive technical reports. But by late 1944, these examinations had taken on a different character, less about understanding enemy capabilities for tactical advantage, more about confronting the reality that Germany's technical sophistication might not matter if Allied industrial capacity could produce weapons that simply refused to fail. Richter had spent the previous month testing captured Flammenwerfer equipment from the Eastern Front, examining how Soviet flamethrowers had performed in brutal winter conditions that had destroyed so many German weapons. Now this American device represented something different entirely, a weapon system designed from the ground up with the assumption that it would be used by ordinary soldiers with minimal specialized training, maintained under field conditions with limited technical support, and expected to function in environments ranging from Pacific jungles to European hedgerows without significant modification. The testing began with basic inspection protocols. Engineers photographed every component from dozens of angles, measured every dimension with precision instruments, and documented construction techniques that seemed impossibly straightforward compared to German methods. The fuel tanks were simple cylindrical vessels, fabricated from sheet steel and welded together with industrial techniques that prioritized strength over weight savings. German flamethrower tanks used lighter materials and more sophisticated construction methods that required skilled craftsmen and careful handling. These American tanks looked like they could be thrown from a truck and still hold pressure. The ignition system caught immediate attention from propulsion specialists. where German flamethrowers employed hydrogen torch ignition that required careful maintenance and frequently failed in cold or wet conditions. The M2 used a mechanical cartridge-based system that was almost foolproof. 5 ignition cartridges sat in a revolving magazine at the front of the gun assembly, each one a self-contained ignition source that required no batteries, no hydrogen bottles, no delicate torch mechanisms. Pull the trigger, puncture the cartridge, flame ignites. The simplicity was startling. German engineers had considered cartridge ignition systems years earlier, but rejected them as wasteful and logistically complex, requiring constant resupply of cartridges rather than reliance on refillable hydrogen systems. The Americans had apparently decided that logistics and supply were problems their industrial capacity could solve, and that battlefield reliability mattered more than theoretical efficiency. It was a fundamentally different approach to military engineering, one that assumed abundance rather than scarcity, that valued tactical effectiveness over technical elegance. The fuel system examination revealed even more profound philosophical differences. German flamethrowers used carefully formulated mixtures of petroleum and tar, Flamethrower 19, that required precise mixing ratios and temperature-controlled storage. The mixture was effective but temperamental, its performance varying with weather conditions and storage time. Technical manuals ran to hundreds of pages explaining proper handling, mixing procedures, and storage requirements. The M2's fuel tanks were designed for something called napalm. Technical intelligence had provided fragmentary information about this thickened fuel compound developed by American chemists at Harvard University in 1942, but seeing the system designed around it made the implications clear. Napalm was jellied gasoline, a viscous mixture that could be stored for months without degradation, that maintained consistent performance across extreme temperature ranges, and that burned with adhesive properties that made it devastatingly effective against fortifications and personnel. When engineers opened the fuel tanks, still containing residual napalm from its last combat use, the material's properties became immediately apparent. Regular gasoline atomized upon release, creating a fireball that dissipated quickly. This thickened mixture maintained coherence, projecting in a stream rather than a spray, maintaining burning material concentrated on target rather than dispersed in the air. German engineers understood immediately why Pacific combat reports had described American flamethrowers as uniquely terrifying. The fuel clung to everything it touched, burning at temperatures exceeding 1,000 degrees Celsius, adhering to concrete, steel, and human flesh with equal persistence. The pressure system used nitrogen propellant stored in a small tank mounted between the 2 fuel tanks. German systems used compressed air or nitrogen as well, but the M2's regulator was designed with substantial safety margins and nearly foolproof operation. A simple valve, easily operated by the soldier wearing the backpack, no assistant required to open pressure bottles or manage complex release mechanisms. The entire system reflected a design philosophy that assumed soldiers in combat would be tired, stressed, possibly wounded, and needed weapons that functioned reliably despite operator error or battlefield conditions. Engineers documented every specification in meticulous detail. Fuel capacity, 4 gallons of thickened gasoline. Nitrogen capacity, 2 gallons at high pressure. Empty weight, 43 pounds. Loaded weight, 68 pounds. Theoretical burn time, 7 to 10 seconds of continuous fire. Effective range, 20 to 40 meters depending on fuel thickness and atmospheric conditions. Every number told a story about American priorities and German misconceptions. The German Flammenwerfer 41, by comparison, carried approximately 3 gallons of fuel, weighed 39 pounds empty, and had an effective range of 25 to 30 meters. On paper, the German weapon was lighter, more mobile, theoretically more sophisticated in its engineering. But those advantages meant nothing if the ignition system failed in rain, if the hydrogen bottle ran out mid-mission, if the precision fuel mixture had degraded in storage, or if the operator couldn't quickly replace an empty hydrogen canister while under fire. The first firing test was scheduled for October 3, 1944. Richter and his team had spent a week preparing the weapon, cleaning residual napalm from the fuel system, fabricating compatible fuel based on captured technical documents, and ensuring all safety protocols were in place. The testing range at Kummersdorf had facilities specifically designed for flamethrower evaluation, concrete bunkers with observation ports, target structures representing various fortification types, measurement equipment to record flame temperature, velocity, and effective range. The morning air carried the sharp smell of autumn, dry leaves, and cold earth, as technicians filled the M2's fuel tanks with their approximation of napalm, a mixture of gasoline and aluminum soap compounds that had taken German chemists 3 attempts to formulate correctly. The nitrogen tank was charged to specification, 400 pounds per square inch, pressure that made German engineers nervous given the weapon's basic construction and minimal safety features. Richter donned the backpack himself, understanding that true evaluation required experiencing the weapon's handling characteristics firsthand. The weight settled across his shoulders and back, distributed through simple canvas straps that seemed inadequate for combat use, but held the load securely. The gun assembly felt crude in his hands, a metal pipe with 2 pistol grips and trigger mechanisms that had no refinement, no sophistication, just brutal mechanical simplicity. At 30 meters distance, a concrete block structure represented a fortified position. Richter opened the nitrogen valve, hearing the hiss of pressure equalizing through the fuel tanks, feeling the slight increase in weight as the system pressurized. He aimed the gun assembly at the target, depressed the rear trigger to release fuel flow, then squeezed the front trigger to fire the ignition cartridge. The weapon roared, not the sharp crack of German flamethrowers with their hydrogen torch ignition, but a deep, throaty roar like a blast furnace opening. Napalm erupted from the nozzle in a coherent stream of burning gel that traveled the full 30 meters and splattered across the concrete block in a cascade of adhesive fire. The flame didn't dissipate or blow away in the wind. It stuck, burning with intense heat that immediately began discoloring the concrete, creating a pool of fire that continued burning for 30 seconds after Richter released the triggers. Every German engineer watching understood what they were seeing. This wasn't incremental improvement or tactical refinement. This was a fundamental reimagining of what incendiary weapons could achieve. The napalm's behavior changed everything. German flamethrowers created impressive but brief fire effects that depended on continued fuel application to maintain effectiveness. This American weapon created pools of adhesive flame that continued burning long after the initial burst, that couldn't be easily extinguished, that turned defensive positions into ovens. Richter fired again, this time at a wooden structure representing a bunker entrance. The napalm stream punched through the opening and splattered across the interior walls. Through observation ports, engineers watched as the adhesive fire spread across every surface, burning with such intensity that the wooden structure began collapsing within 45 seconds. No German flamethrower achieved effects like this. The difference wasn't just quantitative, it was qualitative, a weapon that didn't just threaten defenders with fire but created conditions that made defensive positions completely untenable. The third burst targeted a steel door representing an armored installation. The napalm splattered across the steel surface and continued burning, the adhesive properties keeping the gel in contact with the metal long enough for heat transfer to begin raising the interior temperature. German tests with conventional flamethrower fuel showed that defenders could simply wait out the attack behind steel barriers, but this napalm continued burning for so long that anyone inside would face either being cooked by radiant heat or opening the door to escape, exposing themselves to small arms fire. After 7 bursts, the fuel tanks emptied with a characteristic sputtering sound, exactly as technical specifications predicted. 7 seconds of actual burn time distributed across multiple firing sequences. Richter set down the weapon, his arms aching from the weight and recoil, his face flushed from radiant heat, his mind racing with implications. "Test all ranges," he ordered quietly. "I want maximum distance measurements, flame, temperature profiles, adhesion characteristics, burning duration after fuel cutoff, and thermal penetration data for concrete and steel barriers." The systematic testing continued through the week. Engineers measured everything, documenting flame velocity at 12 meters per second, impact temperature exceeding 1100 degrees Celsius, adhesion to vertical concrete surfaces for more than 30 seconds, continued burning for up to 1 minute after cessation of fuel flow. Every measurement confirmed what the first test had revealed. The Americans had created something that rendered German flamethrower doctrine obsolete. At 40 meters maximum range, the napalm still reached targets with sufficient velocity and volume to create effective fire pools. German Flammenwerfer 41 weapons struggled to reach 25 meters under optimal conditions and typically achieved only 20 meters in actual combat. This American weapon could engage targets from positions that provided better tactical cover, could reach fortifications that German assault pioneers would need to approach suicidally close to attack effectively. The reliability testing proved even more damning. Engineers subjected the M2 to conditions that regularly disabled German flamethrowers: mud immersion, sand exposure, temperature extremes, rough handling, prolonged storage. The weapon continued functioning. The cartridge ignition system worked after being submerged in water. The fuel system maintained pressure integrity after being dropped from a truck. The nitrogen regulator functioned across temperature ranges from -10 to +40 degrees Celsius without adjustment. A German Flammenwerfer 41 brought in for comparison testing failed its hydrogen ignition system after exposure to morning dew. The delicate torch mechanism required disassembly and careful cleaning before it would function again, exactly the kind of maintenance burden that made German weapons difficult to keep operational under field conditions. The American weapon simply worked, regardless of conditions, regardless of operator skill level, regardless of maintenance history. The psychological impact on German engineers was profound. For 5 years, they had consoled themselves with the belief that German technical superiority would compensate for Allied material advantages. Yes, the Americans could produce more weapons, but German weapons were better engineered, more effective per unit, capable of achieving results that Allied equipment could not match. This M2 flamethrower destroyed that comfortable assumption. It wasn't better engineered, it deliberately rejected sophisticated engineering in favor of brutal reliability. And that reliability made it more effective than anything Germany had fielded. Richter compiled his findings into a comprehensive technical report, documenting every specification, every test result, every comparison with German equipment. His conclusions were carefully worded but impossible to misinterpret. The M2 flamethrower represented a significant advance in portable incendiary weapon design. Its use of thickened fuel, particularly napalm composition, created tactical capabilities that exceeded German weapons by substantial margins. Its simple, robust construction enabled operational reliability that German equipment could not match under field conditions. Its design philosophy prioritized practical effectiveness over theoretical optimization, an approach that had resulted in a weapon superior in nearly every combat-relevant metric. But Richter's report also contained observations that went beyond technical specifications. He noted that the weapon's weight and crude construction suggested American confidence in their soldiers' physical conditioning and tolerance for discomfort. The cartridge ignition system, wasteful as it appeared, indicated an industrial capacity that could afford to supply consumable components to frontline units without concern. The napalm fuel composition represented a level of chemical research and manufacturing sophistication that contradicted the weapon's mechanical simplicity, suggesting that American engineering could be sophisticated when necessary, but chose simplicity when it improved combat effectiveness. Most disturbingly, the weapon's very existence and widespread deployment demonstrated that Americans had solved problems German engineers hadn't fully recognized they needed to solve. German flamethrower doctrine emphasized elite assault units, specialized training, careful maintenance, and tactical employment under controlled conditions. American doctrine, as evidenced by this weapon's design, assumed ordinary Marines would carry flamethrowers into chaotic Pacific Island combat, that maintenance would be minimal and performed under fire, that weapons needed to function after being exposed to salt water, jungle humidity, volcanic sand, and the accumulated abuse of sustained offensive operations. The Americans had designed for war as it actually existed, not war as doctrine described it. and their industrial capacity allowed them to produce these weapons by the thousands, equipping entire divisions with incendiary capability that Germany could only provide to small, specialized units. By 1944, Marine divisions in the Pacific carried nearly 250. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. M2 flamethrowers into combat, distributed throughout infantry regiments, available for tactical employment at company and battalion level. German assault pioneer battalions, by comparison, fielded perhaps 24 flamethrowers, concentrated in specialized units that required careful coordination to employ effectively. The report reached Berlin in mid-October, circulating through Wehrmacht High Command with the bureaucratic efficiency that still functioned even as the Reich crumbled. Generaloberst Alfred Jodl read it twice, his annotations growing sharper with each page. In the margins, he wrote a single phrase that captured what every senior officer understood but few would say aloud. "We are fighting the wrong war with the wrong assumptions." The Chemical Warfare Service requested additional testing, specifically combat scenario simulations that would reveal how the M2 performed under conditions replicating actual battlefield employment. Richter returned to Kummersdorf in November with a team of assault pioneers, veterans from both Eastern and Western fronts, who had combat experience with German flamethrowers and had faced Allied incendiary weapons in battle. These men provided perspective that pure engineering analysis could not. They strapped on the M2, moved through obstacle courses while carrying the 68-pound load, practiced quick engagement techniques against fortified targets, and evaluated the weapon's tactical utility from a soldier's perspective rather than an engineer's laboratory. Their conclusions were unanimous and devastating. They would trade their Flammenwerfer 41 weapons for this American device without hesitation, despite its greater weight, despite its crude construction, despite everything German doctrine said about mobility and technical sophistication. Unteroffizier Heinrich Müller, who had carried a Flammenwerfer 41 through Stalingrad and knew incendiary warfare as intimately as any man alive, put it simply: the German weapon is like a finely crafted watch that stops working when you need to know the time. This American device is like a hammer. It is heavy, it is crude, but when you swing it, something breaks. In combat, I choose the hammer every time. The napalm technology particularly fascinated German chemists, who examined the captured fuel residue and attempted to replicate its properties. What they discovered was humbling. American chemical research had achieved sophistication in gel formulation that Germany had not approached, despite years of work on incendiary compounds. The napalm mixture achieved optimal viscosity for projector weapons, maintained stability across temperature ranges, resisted separation during storage, and burned with characteristics that maximized both temperature and duration. German chemists had focused on fuel mixtures that emphasized immediate heat generation, creating impressive fireballs that looked devastating but dissipated quickly. American researchers had pursued adhesion and sustained burning, creating compounds that looked less impressive initially but continued destroying targets long after application. It was another example of how American military research prioritized practical combat effectiveness over theoretical performance specifications. The development history of napalm, pieced together from captured technical documents and intelligence reports, revealed a research program that embodied everything German engineers found simultaneously impressive and incomprehensible about American military-industrial organization. A Harvard University chemistry professor named Louis Fieser had developed the compound in 1942, working in a university laboratory funded by government research contracts, collaborating with petroleum companies and chemical manufacturers, testing formulations on a football field behind the Harvard Business School. This casual mixing of academic research, corporate expertise, and military requirements, all coordinated through flexible contracts rather than rigid bureaucratic structures, had produced a revolutionary incendiary compound in months. German military research, by comparison, operated through formal hierarchies, strict compartmentalization, and doctrinal oversight that often stifled innovation in pursuit of theoretical purity. The Americans had solved a practical problem with practical methods, and had done so with a speed and effectiveness that Germany's more sophisticated organizational structures could not match. By December 1944, Kummersdorf had tested the M2 extensively enough to understand not just what it did, but what it represented. The weapon embodied American industrial philosophy applied to military requirements, design for reliability over sophistication, prioritize practical effectiveness over theoretical optimization, assume abundant supply chains rather than scarcity, and trust ordinary soldiers to operate complex equipment with minimal specialized training. Every aspect of the M2's design reflected these principles. The cartridge ignition system was wasteful but foolproof. The heavy construction was inefficient but nearly indestructible. The simple operation required minimal training but enabled rapid tactical employment. The napalm fuel was expensive to manufacture but devastatingly effective. German engineers, trained to optimize for efficiency and elegance, found these design choices almost offensive in their pragmatism. Yet the weapon's combat effectiveness was undeniable. Intelligence reports from both fronts confirmed what testing revealed. In the Pacific, Marine Corps flamethrower operators were clearing Japanese bunkers and cave positions with efficiency that exceeded anything German assault pioneers achieved with their Flammenwerfer weapons. American after-action reports described single M2 operators neutralizing defensive positions that would have required entire infantry platoons to reduce using conventional weapons. The psychological impact on Japanese defenders was so severe that some chose suicide over facing flamethrower attack, recognizing that no fortification offered protection against napalm's adhesive burning. On the Western Front, American infantry units employing M2 flamethrowers had broken through German defensive positions in France with tactics that seemed wastefully direct by German doctrinal standards. Rather than careful maneuver by specialized assault units, Americans simply assigned flamethrowers to infantry companies, provided basic training, and allowed tactical commanders to employ them as needed. This decentralized, flexible approach meant flamethrowers were available whenever tactical situations required them, rather than waiting for specialized assault pioneers to be brought forward through formal command channels. German doctrine emphasized concentration of force, specialized units, careful coordination. American doctrine emphasized distribution of capability, flexible employment, tactical initiative. In the industrial warfare of 1944, with its emphasis on sustained operations across vast fronts, the American approach proved more effective. A weapon that any infantry company could employ immediately was more valuable than a theoretically superior weapon available only to elite specialized units requiring careful coordination to deploy. Richter's final supplemental report, submitted in January 1945 as Soviet armies advanced toward the Oder River, contained observations that went beyond technical analysis into strategic assessment. He noted that the M2 flamethrower exemplified American military-industrial capability in ways that infantry rifles, tanks, or artillery could not. Every aspect of its design and deployment demonstrated American confidence in their industrial capacity, their chemical research sophistication, their ability to train soldiers rapidly, and their willingness to accept tactical methods that would seem wasteful to German planners, but proved effective in sustained combat operations. The weapon's existence in such quantities, Richter wrote, proved that American industrial mobilization had achieved capabilities Germany could not match. Producing effective napalm required sophisticated chemical manufacturing at industrial scale. Fabricating reliable pressure tanks required precise welding and quality control across thousands of units. Distributing these weapons throughout multiple divisions required logistics networks capable of supplying specialized fuel and replacement cartridges to units scattered across two major theaters. Germany lacked the industrial capacity, the chemical sophistication, the logistics infrastructure, and the raw material availability to replicate any aspect of this system, even if German engineers had designed superior weapons, which Richter's report made clear they had not. But the report's most damning assessment concerned what the M2 revealed about German military leadership's fundamental misunderstanding of modern industrial warfare. German doctrine had emphasized tactical excellence, operational art, and technological sophistication as force multipliers, that would compensate for material disadvantages. The assumption was that superior German weapons, operated by better-trained soldiers following more sophisticated doctrine, would achieve results that Allied material superiority could not overcome. The M2 flamethrower demonstrated the flaw in this thinking. American weapons weren't necessarily inferior. They were designed according to different priorities that proved more relevant to actual combat. American soldiers weren't less capable. They were trained to operate weapons that functioned reliably rather than weapons requiring specialized expertise. American doctrine wasn't less sophisticated. It was optimized for conditions of material abundance and industrial depth rather than scarcity and technical excellence. Germany had designed its military for the war it wanted to fight. Short, decisive campaigns where technical superiority and tactical excellence would achieve rapid victory before industrial disparities became relevant. America had designed its military for the war that actually existed. Sustained global conflict, where industrial capacity, logistical depth, and the ability to equip mass armies with reliable equipment would determine outcomes over years of attritional warfare. By January 1945, this distinction mattered desperately. German forces were contracting on all fronts, fighting defensive battles with dwindling resources against enemies whose material advantages grew monthly. Technical sophistication offered no solutions to strategic problems rooted in industrial inadequacy. The Flammenwerfer 41 was a perfectly competent weapon for a military that no longer existed, designed for offensive operations by elite assault units in short campaigns. The M2 was a brutally effective weapon for the war America was fighting. Sustained operations across multiple theaters by mass armies, supplied by industrial economies operating at full mobilization. Richter's report ended with a recommendation that senior leadership would never implement but needed to hear. Germany should abandon attempts to match Allied industrial output through technical sophistication and instead focus limited resources on weapons and tactics suited to defensive operations by a force whose industrial base was collapsing. This would mean accepting that German weapons would be inferior to Allied equipment in many categories, that German soldiers would face enemies with material advantages that training and doctrine could not overcome, and that ultimate defeat was probable, regardless of tactical excellence. The Wehrmacht continued pursuing advanced weapons programs that consumed scarce resources, training specialized units for operations that were no longer tactable, and insisting that technical superiority would somehow compensate for industrial collapse. By March 1945, as American forces crossed the Rhine and Soviet armies prepared for the final assault on Berlin, Kummersdorf began destroying its research materials to prevent them from falling into Allied hands. The captured M2 flamethrower, still bearing scorch marks from Pacific combat, was moved to storage along with other foreign weapons awaiting disposal. Engineers catalogued it one final time, photographing every component, recording every specification, preserving technical drawings that might have value in some hypothetical post-war future. The weapon had taught them more than any intelligence report could convey about American industrial capability, military philosophy, and the fundamental nature of modern warfare. When American forces reached Kummersdorf in late April, they found the testing facilities largely intact but abandoned. Among the captured documents were Richter's reports on the M2 flamethrower, complete with detailed technical analysis and brutally honest strategic assessments. American intelligence officers who read these reports recognized them as among the most perceptive German analyses of Allied military capability produced during the war, documents that understood not just weapon specifications, but the industrial and philosophical foundations of American military power. The M2 flamethrower itself was recovered and eventually shipped back to the United States, where it was stored in an Aberdeen Proving Ground warehouse, alongside other captured German analyses of American equipment. In the post-war era, when Cold War military planners studied what lessons could be learned from World War II's industrial mobilization, Richter's reports were circulated as examples of how defeated enemies had perceived American strengths more clearly than American planners sometimes did themselves. The weapon's legacy extended into post-war German military thinking. When West Germany established the Bundeswehr in the 1950s, procurement officers and doctrine writers consciously applied lessons learned from studying Allied equipment during the war. German military planners emphasized reliability over sophistication, practical effectiveness over theoretical optimization, and the ability to maintain high operational readiness rates under field conditions. The Bundeswehr's weapons reflected these priorities, favoring robust designs that ordinary soldiers could operate and maintain, rather than sophisticated systems requiring specialized expertise. This philosophical shift owed much to humbling experiences like Kummersdorf's M2 testing, moments when German engineers confronted evidence that their assumptions about technical superiority were not just wrong, but counterproductive. The Americans had won not despite their seemingly crude pragmatism, but because of it. Because they understood that warfare at industrial scale rewarded reliability, availability, and the ability to equip mass armies with effective weapons more than it rewarded technical sophistication concentrated in elite units. The M2 flamethrower saw extensive use in Korea and Vietnam, serving American forces for 2 more decades with minimal modification. Its design proved so fundamentally sound that replacement programs struggled to develop weapons offering meaningful improvements. Eventually, changing tactical doctrine and concerns about the weapon's humanitarian implications led to its retirement. But its operational effectiveness was never in question. The napalm compound, meanwhile, achieved notoriety that its original developers never anticipated. Used extensively in Vietnam for both ground-based flamethrowers and aerial incendiary bombs, it became a symbol of American military power's most destructive aspects. The same adhesive burning properties that made it devastatingly effective against fortifications made it horrifying when used against personnel or civilian targets. By the 1980s, international protocols restricted incendiary weapon use, and napalm's reputation shifted from military innovation to controversial weapon requiring strict employment controls. But in 1944, at Kummersdorf, German engineers examining this captured American flamethrower understood only that they were confronting a weapon that embodied everything their nation lacked: industrial depth, chemical sophistication, pragmatic design philosophy, and the confidence to build weapons assuming abundant supply chains and capable soldiers, rather than scarcity and elite specialists. Every test, every measurement, every comparison with German equipment revealed the same uncomfortable truth. America was fighting a different war than Germany thought was being fought, and American weapons were designed for the war that actually existed. The M2 didn't win battles through technical superiority. It won through reliability, effectiveness, and availability, 3 attributes that mattered more than sophistication when industrial economies clashed in sustained global conflict. Richter survived the war, working afterward as a chemical engineer in West Germany's rebuilding industries. He never spoke publicly about his work at Kummersdorf, but colleagues who knew his wartime service said he maintained one conviction from those testing days: that understanding your enemy's strengths mattered more than believing in your own superiority, and that sometimes the most important lesson a weapon could teach was how much you had misunderstood the nature of the war you were fighting. The M2 flamethrower taught that lesson with brutal clarity. Every burst of adhesive napalm, every reliable ignition under adverse conditions, every measurement demonstrating superior range and effect, confirmed what German engineers already feared: that technical sophistication was not enough, that industrial capacity ultimately determined modern warfare's outcomes, and that American pragmatism had created weapons more effective than German engineering could match. By the time that lesson was fully learned, it was far too late to matter. The war was ending, the Reich was collapsing, and the weapons that might have made a difference would never be built. All that remained were the reports, the measurements, the photographs, and the uncomfortable knowledge that Germany had lost not just battles, but the fundamental competition between industrial philosophies, between sophistication and reliability, between what military planners thought war should be and what it actually was. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.